Let's start learning about the material in Unit 1. Unit 1 is about motion and forces. Lesson 1 is motion in 1 and 2 dimensions. A dimension is like horizontal or vertical. Those are 2 different dimensions. And then like if you have an X and Y graph, X is 1 dimension, Y is 1 dimension. So a dimension is actually 2 directions. It could be forward and back, left and right. When we talk about motion in 1 direction, or in 1 dimension, when we talk about motion in 1 dimension, we might be talking about something like a train moving forward or back along its tracks, but it can't turn off the tracks. Let's look at this image. We should have looked at it in class already. We see photos that were taken of a skier at equal time intervals. So these might be 1/10 of a second apart, or I don't know how fast a jumping skier moves. Let's just say they're 1/10 of a second apart. How would you describe this image? If you were just describing physically what this picture looks like, think about how you would describe it to somebody else. Can this picture be used to predict where the skier will be next? We can tell from this picture that the skier is jumping from left to right, probably not jumping backwards from right to left. And we can see that even though the skier's body is twisting, its center, the center of the body, follows a smooth curve. We watch the center, and I'm not drawing a perfectly smooth curve, but you can see it. So could you use this curve to predict where the skier might be next? And you may be thinking, yes, of course I could, because I could extend that drawing even further, and I can see that these are even intervals from left to right along the center of the skier's body. So if I wanted to know 1/10 of a second where that skier would be, I would go the same interval over and say, okay, my skier is here. And this is exactly what that person would look like on the next twist. We started talking about frame of reference. A frame of reference is some kind of system through which you can clearly describe the position or the motion of an object. So on a map, usually we say north is up, south is down, west is left, and east is to the right. If we have a map like this, and let's say you are at position A, and you're trying to describe to your friend on the phone how you get to the library. Well, from your perspective, from your frame of reference, you would say, I'm going to walk down the street, and then I'm going to turn left, and that'll take me to the library. But for the other person, for the person at position B, if they follow those directions, go down the street, turn left, and keep walking, they're going to end up at the town hall. So the frame of reference for person A is different from the frame of reference, or the point of view of person A is different from the point of view of person B. So you need to have some sort of a frame of reference that works for both of these people. You can't say, I'm going to go forward and then turn left. It just doesn't work for both of them. And that's why we use cardinal directions like north, south, east, west, or at least you need to know what the person's starting point is if you're going to use directions like forward, left, right, and back. Motion always needs a frame of reference if you're going to describe it, because motion only happens relative to something else. If there was nothing else around you, if you were floating empty in space, it would be impossible to describe your motion because there's nothing else to compare it to. So motion is described within some kind of a frame of reference. And a frame of reference is a system of coordinates that has a fixed origin. In this case, it's 0, 0, right? This is what we call a Cartesian frame of reference, or Cartesian coordinates. And you've seen this in math class. And we can add a third dimension here to describe the position of something in space. We can describe it as, we can have x, y, z coordinates. And z would represent the depth going in and out of the screen. When we're talking about directions along a flat surface, along a map, along the surface of the Earth, we use what's called cardinal directions. The cardinal frame of reference, where we have north, south, east, and west, where north is pointing toward the North Pole, south toward the South Pole, and then east and west are relative to north and south. So east is to, I guess we could say it's 90 degrees to the right of north, and west is 90 degrees to the left of north. This is one of your vocabulary terms, displacement. Displacement is a change in position within a frame of reference. So it could be 10 meters north. It can be 5 meters west. It can be 6 meters in the x direction. You have to know what your frame of reference is in order to describe your displacement, because displacement has magnitude, a size, and it has a direction. So displacement describes the change from initial position to final position. You say, okay, here's the final position, and to find what the displacement of something is, you do the final position minus the initial position. You can describe motion using distance, direction, and time. Okay, if we want to talk about speed or velocity, we need to include time in that description. When you have and again, this is another vocabulary word, when you have a quantity that has both size and direction, that's called a vector. So a vector can be 2 meters up, 3 meters west, 5 meters in the x direction. It has a size, magnitude, 5 meters is the magnitude. And then north, south, east, west, x, y, z, those are directions. Not everything is a vector. Like if something is 200 grams, well, that's mass. Mass doesn't have direction. Mass is just how much matter something is made of. If we say it's 80 degrees Fahrenheit outside, well, that doesn't have a direction. So that's a measurement that does not have a direction. It's not a vector. It's what we call a scalar. That's not a vocabulary word, but it's called a scalar. You can use a number line to model a random walk. If you stand on a number line that's numbered out in meters, so you stand at the origin, you stand at 0, you have 1 meter to the right, 2 meters to the right, 3 meters to the right, 1 meter to the left, 2 meters left, 3 meters left, etc. Then you can flip a coin, and this is actually in your textbook on page 8. So it describes it in writing if you want to read it. You can model this random walk with a number line. If you stand at the origin and then you flip a coin and say, if the coin is heads, I'm going to move 1 meter right. And if the coin flip is tails, I'm going to move 1 meter left. Well, in this coin flip activity, if you move left, right, then that means you flipped, you got tails, heads, heads. So you went 2 meters left, then 1 meter right. If we look at it on a number line, let's look at it on a number line. Let's draw a number line. Okay, here's a number line. Here's the origin. If you moved left, and then you moved, so you moved left, and then you moved right, and then you moved back left, and then you moved back right, then you would end up right here. What's the distance you traveled? Well, you moved, so how far did you walk? Well, you walked 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, because you kept going back and forth. So your distance the distance you traveled, your distance was 5 meters. But your displacement, remember your displacement is only your final position minus your initial position. So here's your final position. Here's your initial position. So your displacement, this is -1, and this is 0. So -1 minus 0, your displacement is -1 meters. And I said displacement has direction. That negative sign tells us the direction. Okay, so you can say -1 meters, or you can say 1 meter to the left. There are different ways to describe that. So distance and displacement are not necessarily the same thing. Displacement is just the final position minus the initial position, whereas distance can be all the distance that you traveled through. You might want to experiment with this at home. Again, this is on page 8 in your book. Get a family member and try it. Try to do 10 coin flips and see what your results are like. How far do you end up from the origin, and how far do your family members end up from the origin? You don't have to use meters. You can use feet. Now, the more you do this, the more. If you just do a few tries like we did in this example, then there's a good chance you'll end up away from the origin point. But what would happen? Think about what would happen if I did this 100 times or 1,000 times. Would I be likely to end up farther away or closer to the starting point? It's an interesting thing to think about. Here we have a stop motion photograph. Stop motion. That's the wrong term. But we have a photograph of a sprinter that was taken at equal time intervals. So if we look at this sprinter, velocity is speed in a particular direction. That was a vocabulary word, right? So the velocity over the time interval is the displacement. Velocity, you can say, and this is on your formula sheet, velocity equals displacement. Actually, I'm not going to write it like that. Okay, velocity equals, remember displacement is a change in position. So I'm going to call it velocity is a change in position. Delta is this triangle. This triangle is delta. And delta means change. So velocity is a change in position, change in x, over a change in time. So it's how much did your position change in a certain amount of time. That is the definition of average velocity. The displacement of an object, delta x, divided by the time interval, delta t, divided by that time interval. So this sprinter is photographed at equal time intervals. What do we see? We see, well, in this first time interval, the sprinter goes this far. I'm going to use it. And then in the second time interval, this far. In the third time interval, this far, then this far. What's happening to my lines? They're gradually getting longer. Okay, the lines are getting longer. So these are equal time intervals. Remember, delta t is the same at point 1 and point 2 and point 3 and point 4, but delta x is getting bigger. Okay, delta x is getting bigger. These lines represent the sprinter's displacement. And as the displacement gets bigger, as the time interval stays the same, the velocity increases. So when the velocity increases, we say that person has a positive acceleration. We would graph that person's motion. If we graph their position versus time, we would get a graph that looks like this. But if we put a straight edge on here between t equals 0 and t equals 2, we would get a line like that. Okay, the slope of this line is equal to a change in position. Remember slope, if you remember from math, slope equals change in y, the rise, over change in x, the run, rise over run. Well, y represents position, x represents time. So in this graph, a position versus time graph, delta y over delta x, is the same as saying a change in position over a change in time, which is the same as saying velocity. Okay, so the slope of this line, this straight line, is equal to that runner's average velocity over that time period.